David here. Welcome to the channel. Today is all about systems in flux. If you want to learn more about the science of systems, you can download the book at davidsugar.com/book. There you can get a free PDF. You can also go to Amazon to buy the paperback and you can see all the images in person. So this is chapter 6, all about systems in flux. So what is an equation for a system of flux? One way this could be thought about is that when the change of a quantity x does not equal 0. And now the change of a quantity, like we reviewed in the last presentation on chapter 5, is that when the change is the change from the final state minus the initial state. So when there's a change, it means that the final state is different than an initial state. That they're not the same, that the change in them is not equal to 0. Maybe it grows, it maybe decreases, but it does not stay the same. So the final initial state are different. Now, there's a lot of different types of flux. These are very broad categories, and we're going to go into more different types. One is kind of a linear flux, and this could be thought about as diffusion. A steady decrease, a steady dispersal across the environment, or the increase of entropy tends to just increase over time. So it's a kind of a linear means of flux. There could also be cyclical fluxes, and this is seen a lot with different wave patterns. That a harmonic oscillator, it repeats back and forth, maybe the cycle of the sun, the cycle of the moon. Now, nonlinear flux, they don't sum easily like linear equations. And maybe could be thought about as a tornado or convection currents, where there may be some cyclicalness in it, but it's not a perfect cycle. And there's often this nonlinearity, which makes it difficult to predict. There's other aspects of nonlinearity, so we'll get into that. And so these broad categories can help understand different types of flux, and we'll get into more specifics of each case. Now, one of the most common types of changing systems, a system in flux, is a growth equation. And this could often termed as exponential growth. And in this case, the change in the quantity, so dx divided by dt, the change of the quantity x over time, equals k times x, the quantity. Now, k is greater than 0, so the constant is greater than 0. So this could reflect, for example, investment returns. So let's say that there's an investment and a growth rate like 10% per year. Well, we'll see that it grows on this exponential path. When there's more investments, then it grows more. When there's more investments, then it grows even more. And so this is reflected that the change of x, like money over time, is proportional to x as well as is constant. And in growth, the constant is positive. Now, decay is basically the opposite, where the constant is less than 0. And this kind of creates a scenario where at first there's a big amount, but then it decreases and it gets slower and slower and slower, and it decreases slower and slower amount because there's less and less x, so it decreases less and less. It never gets below 0, but it approaches 0. It's also possible for growth and decay to work interactively and to create a balancing effect. And this can be seen in the predator-prey model. Basically, when there's more prey, it can feed more predators. But then when predators increase, it decreases the prey because there's more and more predators that can eat the prey. And then all of a sudden, there's not enough prey to sustain the predators. The predators will decrease, but this gives an opportunity for the prey to increase. But now increased prey, gives another opportunity for the predators to increase, and this creates a balancing effect. So this balancing equation uses two coefficients, A and B or C and D, to create a balance effect of growth and decay. This isn't reflected perfectly in ecological systems, but this is an idealized mathematical way which provides insights to study how different growth and decay factors can balance one another. And this often seen, in different ecologies where different groups of animals balance one another. Now, another really common type of flux in system is the diffusion equation. And this describes how something diffuses. So imagine a red drop of dye. in a bowl of water. At first, if the dye is really concentrated, it will tend to diffuse over time. And this diffusion can be thought about as just like the random motion of particles, and is statistically likely to be in an equilibrium, to be all evenly diffused. This also would explain like the heat diffusion. So this is often called the heat equation. So if there's a center region of the water that is hot, it will tend to diffuse over time. Now, we can describe the diffusion equation using partial differential equations. We looked at it in last chapter. And so you can see the diffusion equation below, which is saying that V is a vector field. So the change in the vector field over time, which is essentially the speed of the field, how fast the field changes, is proportional to the del operator, that's the upside down triangle, squared times the vector field. Now, remember the del operator squared is basically the partial differential equation on each axis. So the partial derivative of x, the partial derivative of y, the partial derivative of z, and the second order. So we saw with Laplace's equation, basically the del squared of a vector field equals 0. So there's no mins or maxes. It's like a flat, like a soap film. Now, this is saying, the diffusion equation is saying the speed of the field, right? How fast the dV divided by dt equals the diffusion coefficient. That's that little kind of alpha symbol, but also the del squared of the vector field. So basically how sharp a min is. So if there's a big deviation, a big bump, it will diffuse faster. If there's a small bump, it will diffuse slower. And what you see is that once the state is not changing over time, so dV divided by dt equals 0, that equals a Laplace's equation, right? Where the del squared of the vector field equals 0. So it settles into the Laplace's equation. But in the meantime, the sharpness of the local max will determine the speed of how fast it diffuses. Now, another really common type of flux in system is the wave equation. And this could be seen as like a simple harmonic oscillator, like a pendulum going back and forth. Now, the amplitude describes how tall the wave is, the wavelength, how long from peak to peak or trough to trough, and the frequency is the time per cycle. So these are often, characteristics used to describe waves. Now, waves can also be understood in terms of a restoring force, where basically the force is proportional to negative x, where x would be the displacement. So if the pendulum went to the right, there would be a force to the left. The pendulum went to the left, there'll be a force to the right. And so this creates a balancing force, and this creates a simple harmonic oscillation. Now, using partial differential equations, we can also describe the wave equation. And this is really similar to the diffusion equation, where you see that on the right-hand side, there's a coefficient k, and then the del squared times the vector field, so the sharpness of the local max. But in this case, it's not the speed of the field like the diffusion, it's the acceleration of the field. And when you plug this in, you can actually, so the acceleration of the field equals how the sharpness of the bump. And this, we're using partial differential equations to explain in multiple dimensions, which we'll see is really useful. Basically, now this defines the wave equation, which is really cool. Now, another solution to the wave equation is to use exponentials. And you can see that on the right-hand side here, where there's kind of a spiral, and this describes the exponential, where there's an imaginary axis along the y, that's the I, and that has a sine function, and the real axis, which should be thought of as x, is the cosine. So sine, cosine are solutions to the wave equation, as well as exponential. So waves are really common. We see this a lot with different sound instruments. So, there's guitars, there's drums, and this shows a tuning fork. So when you hit a tuning fork, there's regions of air that are compressed and not compressed, compressed and not compressed. And this basically translates to sound. And you can draw a wave to kind of understand the frequency of these kind of sounds. And this can describe lots of different things in our everyday world, that creates sounds and vibrations. Now, another way to understand waves is through different harmonics. And so these are called standing waves. And an important part about harmonics is that the endpoints are fixed. So there can be one wave, there can be two waves, there can be three waves, and these are the different modes. So m equals 1, m equals 2, m equals 3. And there's no half modes because that wouldn't allow the endpoint to be fixed because it would either be up or down, not at a node point. So these are only whole number nodes. Now, another way you can do it is to have a circle. And so in this circle, there can be different amounts of modes. So you see m equals 0, 1, 2, 3 describes the different modes on a circular string. And this, would be going back and forth. Now, a really cool part about waves is that they can be easily superimposed. So if you have different waves on top of each other, you can easily calculate the total wave superposition. And this describes lots of the harmonics that we see in like music. So octave, basically it's about combining a wave with the ratios of 2 and 1. So one of the frequencies is twice the other. And then when you combine that, you get an octave. So a low E and a high E, play together and it sounds really good. You can also create a lot of the other kind of musical ratios, like fifths, fourths, like different chords, minor chords. And so these show what the waves look like, right? And so when you add up these waves in superposition, like 3 notes, you can create a harmony. And so this is often seen in music with wave superposition. So wave superpositions, they're really cool. You can do something called like a Fourier transform. And this is a mathematical way to combine different waves. And what's really interesting is any form that's repeated can be described mathematically as a summation of different harmonic modes. So let's imagine a square wave. Well, it seems, how would you describe a square wave with sines and cosines that are smooth kind of bumps? Well, if you add them up in a certain way, you can very, very closely approximate it. And with more and more waves, you can perfectly approximate a square wave. So you can superimpose ones, and this is seen in this graph here. You superimpose different waves of different heights, different frequencies, and then you can get a square wave. So that's one way you can add up waves to get a certain waveform. It could be a triangle waveform like up and down. It could be a square waveform. You can create any type of waveform that you want. So our ears do something like this, but in reverse. Basically, let's say we get a waveform. What our ears do is that certain follicles, hair follicles, are sensitive to different frequencies. And so we may pick out, oh, there's a low frequency. Oh, there's a high frequency. And this is like why harmonies really sound good, right? When you play those 3 notes, you get that full waveform that's superimposed, but then your ear decomposes that. And it says, oh, there's these 3 notes, and they also have relationships between one another. It creates this harmony. So our eyes also do kind of something similar where we see different frequencies of light, and that helps us perceive color. So waves are really essential for us to understand the world, to sense the world. So waves are also seen in natural patterns. Some of the most common ones are the changes of the seasons. So when you look at the sun, this is an example of like the northern hemisphere below the Arctic Circle, but basically the hours in the day will follow a waveform. Well, there'll be the highest amount of hours of sunlight during the summer solstice, the lowest amount of hours of sunlight during the winter solstice, and the equinox are these middle points. Additionally, the moon goes through various cycles, right? Full moon's the brightest, new moon's the least, and the different quarters are the middle points. So waves are really important to understanding the fluxes in nature, how the planets, how the sun and the moon moves around. So waves can also be seen in the tides. So this is just an example of 1 month of tide data. This is real tide data. And you can see there's lots of these different waves that are superimposed to create the total tide effect. There are some, shorter, different changes in the swell, and there's also kind of longer, almost monthly cycles. So there's a lot of different cycles, and you can decompose these tides to understand the simple harmonic waves. And then, you can also use this to predict, in the future, where would you expect this the tide to be in the future by understanding the root waves and projecting that to the future. So the reason why we use partial differential equations, it seems maybe kind of advanced, but we did this because now we can understand waves not just in a line, but on a surface. So let's consider a circular surface. So here there's basically two modes, the radial mode and then the angular mode. So the top example shows a radial mode. There's two. So there's the circle on the inside, the circle on the outside. And the angular mode is just one. So it's fully circular. Now you can do that same radial mode of two, but now have two angular modes, and this creates an X. So these lines can be thought of as the nodal lines. So these are waves, these kind of surfaces are going back and forth, but those lines represent the places that are not moving. So similar to a string, the end points are not moving. Now they're lines because it's a surface. And you can add up these different surface harmonic waves, like we added up the other waves in a Fourier transform. And this shows various nodal patterns that you can get. So when you add up various ways, you can get all these intricate patterns. These are often called cymatics. So what you can do is you can vibrate a circular surface with some sound, for example. And if there's sand on it, the sand will tend to hang out in the regions, the nodal lines, because those are not vibrating, right? Some are vibrating up and down, but the nodal lines are basically staying constant. So the sand will tend to organize around these lines. So this shows all the various harmonies you can make. If you pour sand on this, you put some sound, you would expect to get some of these different wave harmonics. And whatever pattern you do get, using Fourier transform, you could understand what are the root waves, what are the harmonics that sum to that given shape. So you can also do this with a square. So the top shows white and black, and these are different surfaces. So that would be maybe up and down, and these would be going over time. Now below, we're using these nodal lines again. And you can see there's all these intricate patterns that you can get. If you add up different modes, and these modes are along the X and Y axis, so you can get all these intricate patterns. A lot of these intricate patterns are created by adding multiples, so you can see the different parentheses there that are adding some of these different surface wave harmonics to get really interesting patterns. Now, this can also be extended to volumes. So imagine a cube, and now the modes are along the X, Y, and Z axis. So similarly, you can create, there's different modes, vibration in this volume, and those can also be added like a Fourier transform. You can get lots of intricate volumetric patterns. It's actually really interesting because you can also do volumetric cymatics, which is basically that imagine there's sound that's vibrating a volume. And now similarly, little particles like little sand grains will tend to avoid the places that are moving back and forth and will settle into these nodal surfaces. And actually, you can control a little grain of sand, move it up or down, and, it will make these three-dimensional cymatic patterns. So it's really cool. And volumetric symmetries also play a role, we'll see later, in electron orbitals, and they commonly come about in physics. So it's really important to understand these kind of waves and how they can be understood on different volumes, different surfaces. So in nature, one of the most common types of waves is electromagnetic wave, which is also called light. So in this case, there's an electric field and a magnetic field, and they both self-induce each other. And they move along a direction of motion, and they move at the speed of light, which is often used as c. And so there's different wavelengths, there's different frequencies, there's also different energies. And this can describe a lot of the optics that we see, a lot of the properties of light are understood because of their wave nature. So different waves of light can be understood on a spectrum, the electromagnetic spectrum. So high energy waves have a really, really short wavelength. And this can be thought about as gamma rays. And these are around the scale of atomic nuclei. So they're really, really small, and they often are involved with atomic processes. Really long wavelength have a really low energy. And this can be thought of as radio waves. So they're more influenced at the geologic scale. Certain radio waves sound good when you're in the path of the wave, but if you go behind a mountain, you won't necessarily get it because the wave won't be able to curve around the mountain. So the visible spectrum is really interesting in the electromagnetic spectrum because this is the most highly produced spectrum by our sun. So our sun produces tons of visible light. And the organisms on Earth have actually evolved around this, right? So a lot of plants are photosensitive to around this visible light spectrum. And this also kind of makes sense because the visible light wavelength is around the size of cells and like biomolecular processes. Like high energy gamma rays are so small, they're really like knocking out like protons and neutrons of atoms, knocking electrons. So they're so small, it's pretty hard to interact with them. The really, really long wavelength, low energy radio waves, they're so big, they're acting at more of a geological scale. But the visible spectrum is just right at that sweet spot where they can interact, with photosynthesis, they can interact with the eyesight, they can interact with a lot of things. So there's different colors in the visible spectrum like violet, blue, green, yellow, orange, red. And this really comprises all the colors that we see. So wanted to do kind of some intros into quantum mechanics because there's some really interesting parts that the wave nature of light has both a wave and particle attributes. So we saw earlier, the electromagnetic spectrum, it can be described as kind of a wave. And there's different wave properties like dispersion, refraction. You can use lenses to kind of direct light to a certain focal point and lots of cool things like that. And those are all understood in terms of wave nature. But there's also a particle nature of light. And this can be understood as kind of like wave packets where there's like certain little packets of light that are shoot out. And this can often be modeled as particles. So the photoelectric effect is basically that certain wavelengths will excite certain electrons in atoms. And basically this can only be understood if light moves in discrete particles. Because like in a solar panel, only certain colors of light frequencies will have enough energy. So this led physicists to say, what about if you use low energy, long wavelength light? Couldn't you just get the same energy if you pump more and more light into it? Well, no, if the light moves as packets, because each of those packets wouldn't have enough energy. So the energy of the photon basically equals Planck's constant times the frequency. That's one of the equations of quantum mechanics. And the photoelectric effect says, okay, if you have a high frequency like this blue light, each of those wave packets will have enough energy, excite the molecules, and this can explain this, key effect. And there's other reasons why lead one to believe that light can be understood as particles. And so quantum mechanics has this idea of the wave-particle duality where both models can be useful in different cases. So one of the really fascinating parts about quantum mechanics is this notion of the double slit experiment. So this wave-particle duality is not just, limited to light. It's reflected in everything. Now, only something with really small mass or really small momentum would actually have a noticeable wavelength, but technically every mass and every item does have a wavelength. So electrons are a good example. They're small enough where they have a noticeable wave effect, and they also can be understood as particles. So if you pass two particles through two slits, you would expect to see basically two bumps where the particles peak at certain areas. If you pass waves through two slits, you would expect to see interference, where those different waves are interfering with each other, and it creates an interference patterns where there's certain highlighted areas where there's a high amount. Now, the really interesting part is that electrons, when they're shot through two slits, at first they were thought of as particles, but it turns out that when you shoot electrons through two slits, it creates an interference pattern. It basically creates a pattern of waves. So what's really trippy about this is that even when one electron is shot at a time, it still creates wave interference. So this led physicists to kind of scratch their head. Okay, how is it possible? Is the electron going through the top slit or the bottom slit? Is it interfering with itself? So this leads to lots of questions. Now, this is understood in modern quantum theory in terms of there's a probability field, a quantum probability field, and the quantum wave of probabilities goes through both slits, interacts with itself, and then there's an observable outcome at the end, which creates an interference pattern. So in a way, the electron goes through the top slit, it goes through the bottom slit, it goes through both slits, and it goes through none of the slits. All these are probable outcomes, and those waves actually interact with itself to create the observable outcome. Now, what's really interesting is that physicists said, okay, well now I'm going to put an instrument to say which one did it really go through. So if you actually measure which of the slits the electron went through, now it creates the pattern of particles. Well, what happens, we'll find out later when we learn more about quantum mechanics, is basically when you're observing the electron, like interacting with light or like trying to observe it through interaction, it collapses the probability field. So once the probability field is collapsed right before a slit, the wave will only go through one of the slits and makes a particle-based pattern. So basically, when the electrons are not observed, they create a wave of interference. When they are observed right near the slits, it collapses the wave and it says it's only going through one of the slits, and it creates a particle pattern. So this is some of the really interesting parts about quantum mechanics and why it's important to have both a particle and wave-based interpretations. So another aspect of waves in nature, and this also relates to quantum mechanics, is these electron orbitals. So we're talking about these electrons that can be understood at different waves. So the Bohr model basically understands electrons as occupying different different energy levels. So we see here there's E2, the second energy level, and then E3, the third energy level. Now, if an electron, for example, jumps down an energy level, it can release energy in the form of a photon, for example. But also, that photon can be absorbed by an electron, and it can bump electron up an energy level. So what's really interesting about this model, and this was one of the initial models in quantum mechanics, trying to understand the electron orbitals, is that this is similar to standing waves, right? The electron can't have a 2.5 energy level or 3.5 energy level. It has to only exist in these standing modes. Now there's more rules about how many electrons can be in each orbital and all the different variations. But what's really interesting about this is that the wave nature of the electron is essential to understand the properties of atoms, the properties of chemicals. This can't be understood just with a particle-based interpretation. It has to be understood in terms of waves. So a more sophisticated model of electron orbitals uses these spherical harmonics. Now we saw before different wave harmonics in a cube, but now if you have a radius and two angular axes, this would create spherical harmonics. So there's different spherical patterns. These are different harmonic modes in a spherical orientation. And there's different energy levels. There's also different orbital types. So this is like S, P, D, and F. And there's different orientations that these orbitals can be in. Also, there's often different spins. So basically, one electron could be up here, down here, up here, down here, and there can be another spin which is countering that. So it's the opposite orientation. So two electrons can fill different orbitals with the same orbital when they have different spin. So what this basically allowed was to understand more of these wave harmonics. This creates a really, really detailed picture of understanding how electrons are surrounding protons and neutrons and understanding different atoms and basically understanding the periodic table. So the periodic table, not all the elements are written here, but you can see that I've created a legend of the periodic table. And the periodic table, one might say, why are there different rows? What makes all the different columns? Well, those are all about filling these electron orbital levels. So the different rows are different energy levels. And then the different columns are filling up different of these orbitals. Now there's different amounts of electrons per level. different amounts per the different orbital type, like S, P, D, or F. I'm not going to go into all the specifics of this, but what's really interesting to know is that understanding these spherical harmonics gives you a path to understand the entire periodic table of elements. And I'll just say, like, the column on the right-hand side, they're not written here, but this would be like elements like helium, neon. These are often called noble gases. And these noble gases have the entire energy level filled. And once the entire energy level is filled, they're very inert gases, right? So it has enough protons for positive charge to balance all the electrons to fill a given energy level. So it's a very inert. It doesn't really want any more electrons. It doesn't really want to give any away either. So these inert atoms can be used in different cases, but how they're explained by is understanding electron orbitals, different energy levels, and when they're filled. So want to switch gears a little bit to a different type of flux. So we talked a lot about these like linear, like growth, decay, diffusion. We talked about cyclical, like waves. And now I want to talk about different nonlinear. Now, there's a broad class of nonlinear flux. And these are often called like nonlinear differential equations, differential meaning that it's describing how things change over time. But the key aspect of what nonlinearity is about is that it does not follow superposition. So waves, follow superposition. You can easily calculate the total superposition of the waves by each of the harmonic modes, adding them together. But nonlinear systems, nonlinear differential equations don't easily follow nonlinearity. So that would mean like a function of A plus a function of B does not equal the function of A plus B. In a linear case, the function of A plus the function of B does equal the function of A plus B. So with nonlinear, they don't follow superposition. They're really hard to add together. And this creates a lot of these different like chaotic and complex behaviors. So I'm just going to list a few behaviors we see in nonlinear functions of flux, and there are many more. But one is this notion of phase change, where it's behaving at a certain rate, all of a sudden it changes down or changes up. It completely changes its properties, like a different phase, like a certain temperature. All of a sudden it's a liquid or solid. The macro effect is completely different, completely unexpected. There's high sensitivity. And this could be thought of as the butterfly effect. So small changes in initial conditions can create huge macro effects later on. There can be chaos, which is, even though there is a mathematical formulation of how it's followed, there's not an efficiently predictable way to calculate the results. So this means that, a lot of the results are almost impossible to predict. We see this with weather patterns. They're really hard to predict 10 days out. There's so many variables. There could be multi-stability, which basically means different patterns at different macro levels. Aperiodic patterns, which are semi-repeating patterns, but don't perfectly repeat. And even amplitude death, where you see a pattern just completely end for seemingly no reason. So these are all different, these chaotic and complex results that we can see that often come about in nonlinear functions. These are nonlinear differential equations of describing how things change over time. So one of the really interesting types of nonlinear equations is this diffusion reaction equation. These are also called Turing patterns, made by Alan Turing. And basically this is saying there's diffusion of two substances like X and Y, but there's also a reaction on this boundary. So on a certain boundary, it may not let X or it may not let Y pass, but they're still diffusing. And setting different variables, you can see that this graph here shows the two substances as black and white. You can see by setting different coefficients on these diffusion ratios, they start out in a random state, but as they evolve over time, they evolve into a whole myriad of different patterns. So sometimes there's little spots, sometimes there's little stripes. And this creates a lot of patterns that we see on animals. So there's different fish with these different patterns, like in the coral reefs. Different like jaguar spots, different like zebra stripes. So tons of these animal patterns that we see can be modeled through diffusion reaction equations. So this leads one to think that, really simple chemical reactions of just saying, this chemical is naturally diffusing as it normally would, but there's a simple reaction along a boundary, now this can produce a lot of this really intricate patterns that we see in nature. Another type of open flux, and this is a nonlinear flux. And what's important about this is thermodynamic non-equilibrium. So a lot of the patterns we studied so far have been in a state of thermal equilibrium where, there's no energy in or out. We have a bowl of water, a drop of dye, and we're seeing how it diffuses. We're not changing anything. But there's a whole new class of patterns when we look at thermal non-equilibrium. So a really common example is convection currents. So imagine you have a pot of water and it's on a hot stove. So there's heat from the bottom and the top is exposed to air and it's dissipating heat. So heat is constantly flowing through the system. So it's an open system. Now in these open systems, what we often see is that the water creates these circular kind of toroidal fluxes. And these are called convection currents. And this is just created because warm water, it tends to rise to the top, and when it cools, cool water tends to go down. Now, different cells can be created of convection cells, and this can even be seen on the surface of the sun. So when you look at a surface, there's different cellular regions around circular regions that are rising with hot and sinking with cold. Now, convection currents also play a key role in our atmospheric patterns, our weather patterns. So there's the polar cell, the trade winds, other kind of regions on the globe you can see here in the diagram. And this describes how wind tends to move because tons of heat is going onto the earth and it's rising, it's cooling. And so there's these huge convection currents all throughout the atmosphere. They're in the ocean and they're even on the plate tectonics and in the core of the earth. So the mantle, which is all this magma inside the earth, the inner core of the earth is really hot. It's heating up this magma and it's going near the surface of the earth, cooling and coming down. So the convection currents play a key role inside the earth. And as different the magma in the mantle is spreading apart, this often creates different ridges or underwater volcanoes. When they're coming together, this often makes mountains and different volcanoes that can be seen up there. There can also be trenches when the mantle is coming down. So there's a lot of really interesting patterns that can be seen across the earth. It could be seen water, air, this liquid magma, all through convection currents. So I wanted to highlight another really, really interesting type of flux system. This is thermodynamic non-equilibrium again, and these are called dissipative systems. So the key part about dissipative systems is that without continuous energy or resource or matter, they dissipate. So one example is a water vortex. So if water is going down a drain, water often creates this vortex pattern. But once the drain stops moving, then that vortex stops. So the vortex will dissipate. It will only be allowed once there's a continuous flow. So this can be seen in tornadoes, cyclones, where there's this continuous flow of air and energy, and it's creating these vortexes. Now, dissipative systems also have a key relationship to life, because biological systems are open systems. They're continuously ingesting food, energy resources, and this basically creates the pattern. Now, if living systems stop taking these inputs, they would dissipate over time and decay. So they're only able to create order by the open flux of energy and resources. So dissipative systems is one of these really interesting fields when it comes to thermodynamic non-equilibrium, open systems, and it really understands how is structure, how is pattern created within a continuous flux. Thanks for tuning in for Chapter 6, all about systems in flux. Really excited that you've been here. And next chapter, we're going to look at symmetry, and this will lead into fractals and lots of other cool things. If you want to download a free PDF of the book, feel free to go to the website, davidsugar.com/book. You can also buy the paperback on Amazon. Thanks for tuning in and see you next time.